Hello to everyone. In this third experiment, you will learn how to control your robot to go from one arbitrary point to the goal position. So the goal is driving robot from arbitrary pose to goal pose. In this experiment, we will use closed loop control for defining robot linear and angular speed, and we will learn something about kinematic of mobile robots. So in order to control a robot, you will need to learn some basic kinematics concepts. And if we have this literal robot with differential drive, like the DaNI robot, we can control speed of its left and right wheel. And if you present this speed with phi r and phi l, the linear speed of robot can be present like this formula at the top, and the angular speed is at the bottom formula. So if you know what speed you want to achieve with your robot, you just solve this equation with two unknown parameters and get speed of left and right wheel. In order to do a closed loop control, we need to transfer to a polar coordinates, and we can transform the coordinates like it's shown on the bottom left of the screen. So you have rho, alpha, and beta coordinates. According to the picture, you can determine rho, alpha, and beta for every position of your robot. It can be shown that the control law, like this linear control law, will drive your robot to your goal position. So the linear speed of robot is k rho multiplied by rho, and the angular speed is given like the formula here. And the closed loop system can be described as this system here, and the parameters k rho, k alpha, and k beta will need to satisfy these equations here in order to have a local stability of this system. So now we will open lab view. We will at the beginning create new VI, and this VI we would save as, so just make new folder, experiment 3, and save this VI with name set speed. With this VI we will calculate the desired speed, linear and angular speed, to achieve the goal position. Okay, now we need to use some clusters. So for the cluster, the first cluster is going to be goal position, goal pose, and the second cluster will be current pose of your robot. As the outputs, we will have two numerical indicators, linear speed and no control and angular speed of robot. We will now import here numeric control, three numeric control. The first is X coordinate, Y coordinate and the orientation of robot. So angle theta. Also, we need these three coordinates in the current pose of robot. Now, we will, from these two positions, calculate rho, alpha, and beta, and with this simple linear control law, we will get the linear and angular speed of robot. So going to block diagram, just see how this data is in. Okay, now we have that in our cluster. Okay, we will first unbundle by name all coordinates like this. Okay, so x, y, and theta. Copy this to pose. Okay, and now calculate. From formula we can see that the rho is s squared t of delta x plus delta epsilon. So we will first find the subtract from x and epsilon and square that. Also we do that for epsilon. Okay, and now sum of these two numbers and square root of that, just to find square root, will give us coordinate rho. Now multiplying that with numeric indicator, so go to front panel, numeric control, rho multiplying car row with row will give us a linear speed of our robot. Now we need to determine the alpha and the angle beta. So we need arcus tangens of our delta epsilon, y and delta x. So now atan 2, atan 2. Pa, jel vidiš? So, okay, we will now need to find arcus tangens function. Okay, mathematics. Go to geometry. Angle. Oh, it's not there. We can search. Just find trigonometrics here inverse tangent, and we put here y coordinate and x, and we have here inverse tangens function. So the alpha is minus theta plus arcus tangens, so minus theta, and the theta is actual current theta position, plus arcus tangens will give here, so here is rho, and here is alpha. The beta we will get if we add these two numbers, so minus theta minus alpha, minus alpha, and adding minus alpha and minus theta. Now our linear speed will be k alpha and k beta. So k alpha, sorry, k alpha and k beta. So okay, k alpha, k beta. The linear speed is k alpha multiplied by alpha plus k beta multiplied by beta. So here is beta. And now we have our angular speed. And now at the end we need to connect inputs and outputs of this signal, so goal position, and current position. Outputs is linear speed and angular speed. And we will set these parameters also as inputs. So K rho, K alpha, and here K beta. So, and save this for later. So at this moment, we have a function for calculating linear and angular speed. At the end, we will just make new block layout. So just use a template like this and type set speed. Okay, and save that. Now open new VI. Also save this VI in experiment 3 and name it new position. New position, okay. With this VI, we will define a new position of robot after one loop of algorithm. So we will need also one cluster to which represents robot current position, which have 3 coordinates like in the previous VI, and put these 3 coordinates in our cluster. Also, in this VI we use as input robot current, linear and angular speed, and angular speed, and also it is an algorithm step, and so how much seconds the one algorithm step is take. dt, and as output we will have a new robot position. So we can copy this, press right click, and then change to indicator and just type this new position. Okay, open a block diagram. Again, unbundle by name. Connect it with so we have 3 robot coordinate, and because the robot has only linear and angular position, we can calculate with that position the local in global coordinate system how much in each coordinate axis the robot is travel. So if we multiply linear speed with cosinus and sinus theta, we will get how much is travel distance in two axes in a plane, and if we just multiply angular speed with this amount of time, we will get how much the change in angle, in orientation. So if we multiply linear speed with cosinus theta, so cosinus theta sinus theta, so cosinus theta multiplied by the linear speed, we will have the speed in x direction, and if we now multiply that with the delta time, we will get the travel distance in that direction. Adding with a previous x position, we will get a new x position, and just we need a bundle by name function. Input cluster is object type position, new position, and we connect new x here. If we want our other direction, multiply sinus theta with linear speed, then multiply that with time, and get the change in other position, in other axis. And if we add these two values, we will get a new position for another coordinate. And as I said, if we multiply angular speed with time and add it with previous angle, we will get a new orientation. And now we have calculating a new position of our robot. We need to connect inputs and outputs. Input robot position, linear and angular speed, and delta time, and as an output, new robot position, changing the icon, use template as before, and type new position, and save this. Now we are going to open a project, new, same as earlier. So okay, we can now close this and create a new project. We'll create a template. So go and create a new project. We will create robotic projects template, robotic environment simulator, as I mentioned before. Click next. And we will find our example 3 project, select that folder, project name, experiment 3, and click save button. Okay, we now enter in our main window, go to block diagram, delete this event structure, connect error, and again add stop button here on the main screen. Okay, now we are ready. In this example, we will use another loop, timed loop, like this, and we will set period as input, and the period will going to be create constant, and the period is 100 milliseconds. As we do before, we're going to use starter kit 2.0. We need to initialize our simulated robot. So now we have our robot ready, and what we need now, we need a steering frame initialize. With this steering frame, we here automatically calculate desired wheel speed from linear and angular speed. Now we will have our initial robot position and goal robot position. In initial robot position with 3 coordinates. Done. And one for goal position. Okay. So these two speeds, positions, and now we want to use our set speed. So we are going to select the set speed VI. We have our goal position. Connect here. And our initial position connect here. We can set this parameter also to be visible on the screen. We will create 3 controls. Like this. As output, we will have our linear and angular speed. So we now can use steering functions. We want to write down speed to motors by using the functionality of the steering frame. Steering frame in, we will connect that here. And steering frame velocity will accept 3 speeds in 3 coordinate axes, but in 1 coordinate axis will always be 0 because of the geometry of our robot. So we will now need to use some array functions like, just to see, build array, just build array function, and we need 3 blocks. The first will always be a 0. One needs to be a linear speed, and another angular speed, and let's go here for steering frame velocity. We just add this here, disconnect from here, and goes there. Now we need, with this we have two speeds, linear and angular, and we're going to write that to motors. We use our robotics function to write down the motor speed. So like this, and now we will use index array function to write down here the speed of left and right motors. Now, because we want to see what is going on our real system, we need to read the achieved speeds as before. We put these functions here, and we read our speed from that, and because we want to see what's happened to our we want to calculate new position, we again going to use steering frame functions, but we want to calculate from motor speed to speed of robot in global frame. Like this, and now we will again build array, like this, and enter the speed here. And now we can extract our desired speed using index array function. We have three coordinates, but the first is always 0. Now we can use our VI new position, now connected like this. Okay, just to add more space here. And now I will connect our initial robot position to here. like this. Linear speed is second, and the third is angular speed. Like this. And we can set here constant 0.1 seconds. As exit, we have new position of a robot. We will use now shift register to achieve always changing position of our robot, and we can plot this to a XY graph. So now we can limit the linear and angular speed. So we need okay, so we need to limit our speed, and we can use this in range block to achieve that. Can we add some space here? Okay. So this is our control signal, and this is corrected signal. And we can limit it with 0.5 and minus 0.5. Also, what we need to do is to guarantee that the program will stop when these two position global initial get to close one to each other. We will do a subtract from goal position and initial position, do the absolute value, and ask if that value is smaller than some predefined value. We are going to create constant and type 0.05 0.05, so 5 centimeters, and 0.05 also for radians. We will now unbundle by name these. So we can ask if these two, or if all of this is achieved, like it, and just check this with all other. Like this. So we will also limit our linear speed using the same rate function, also with the same limits, 0.5 and minus 0.5. Go to front panel, set these values to be like this, and our goal position is these two coordinates. Here we can type a 0. Now run a simulation, and we can here track our progress. So the program is end, and here is our goal position of robot. As I said in previous video, in order to apply this code to your robot, you only need to change this function block and use this one. So robotics starter kit 0.2 and initialize. Once again, thank you for watching.